Hi, today we'll be talking about the particulate nature of matter. For this particular chapter, we'll be learning a few things. Number one, we'll be actually learning how particles are always moving around you and in a constant and random motion using the particulate nature of matter. Second, we will also be talking about an understanding of how the arrangement and movement of these particles occur within the solid, liquid, and gas. We will also, through after understanding this arrangement and movement of the particles, we will slowly explore to explain the movement of such particles when there is actually a physical change of state due to melting and boiling. We will also be seeing how the particles actually move and contribute to the expansion and contraction of um, your solids with the conservation of mass during these processes. We will also compare the solid, liquid, and gas in terms of arrangement and movement of the particles, and slowly try to tie in everything towards how it actually happen or behave in our real daily life. Okay, so without further ado, let's begin. So number one is that what is matter made up of? Okay, matter is made up of tiny discrete particles, so tiny that even our visible eyes we are not able to see, and not say a microscope. So the particle theory of matter describes how what matter is made of and also how it actually behaves. So do know that particles are always in constant and random motion, and that diffusion, okay, is the way in which we are able to visualize to see how such particles are always moving. Okay, it may not be the best way, but this is definitely one of the way, at least in secondary school, where we are able to see. And diffusion is constrained usually at the liquid state and gas state. Okay, so what is diffusion? It is the overall movement of particles from a region of high concentration to a region of low concentration. To illustrate this point, let's look at this particular box here in the middle. Okay, where the dots represents the particles, the green spot represents the particles, and the box represents the space in which it resides inside. So what actually happens is, if you can see the area that is highlighted in yellow, that's where there is a high concentration of particles. Okay, and slowly, if you look at the other side of the box, the green area, you realize that this actually has a region where there's empty space and there is low concentration of particles. So what happens is these particles will start to move around randomly, but it will not just move randomly and all over the place. It will move all over the place, but eventually it will actually locate at the area where there is low concentration. So it can be in any part of the room, such that everywhere eventually it will balance out. Where it will slowly balance, where it will slowly balance out to ensure that the room has all the particles equally distributed at all of the space. And at the same time, it is always in constant motion. It will not grow bigger or smaller. That's basically the sensitivity of how my iPad is like. But what happens is there's always this movement. So it will slowly distribute. So it will move towards an area that there is lower concentration. So you can see initially there was very high concentration at this particular area. Now it's not. Okay. So that is what diffusion is. So for the particulate nature theory of matter, it follows four main principles. The first one is that particles are very small and invincible. Now, when we say invincible, we do not say that it is transparent. We actually say that it is too small for the naked eye to be able to see, even with the use of a microscope. Okay, so just take it that the particles are very small, but that doesn't mean that it is in non-existent. Something is just there, just that we couldn't see it and use with the technology now. Secondly, is that between these particles, there are also spaces. So in a way, let's look at some. I can draw a very simple, again, the box. You have multiple particles all over. So the spaces are all these region, these empty spaces that the particles can actually move around. So that is what they meant by spaces between the particles. Okay, so from here to here, these are the spaces. And that the amount of space between the particles differ in a solid, liquids, and gas because later on you'll be looking at how the particles are being arranged in these three states. Next, we look into the third point is that these particles are always moving. Like what we saw, it's always in constant and random motion. So it moves us at very different states of metal, which is the solid, liquid, and gas. So what is this contributed mainly by? It's mainly contributed by kinetic energy from heat energy. So what is kinetic energy? In simple terms, kinetic energy means moving energy, okay? Or energy that allows a particular object to move. And what actually happens is that depend with the amount of space available, these particles can move. So let me give you an illustration. You try to visualize yourself in the classroom. Okay, it's just you alone. You're sitting in the middle of the classroom with a chair that can roll around. Okay, so what happens is you are able to move freely because there's so much space and you are the only particle within it. So that is in the same situation like the gas. And of course, if let's say you have more if I let's say increase the temperature of the room. Okay, now it's like very, very hot, like 45 degrees Celsius. You'll be frantically moving around trying to cool yourself out. So the particles also behave in some of a similar way, where when there's an increase in kinetic energy, it will result in an increase in speed of movement with respect to the availability of space within the particles, within the metal. Now, now slowly imagine yourself in the same room, but I cluttered the whole classroom with chairs and tables. You may still be able to wiggle out and move about with any tiny spaces. So in that sense, right, what we can see is your speed of movement is actually restricted. It becomes reduced. So as we can see from the gas towards the solid, the space available for movement actually decreases, where gas actually has a lot of space for movement as compared to solid. So later on, you also see that in solid, there is practically no movement for you to actually squeeze through the space. But that doesn't mean that the particles do not move. You are still able to move. Like you can move your hands, you can move your legs, but only being confined to the area which is your chair. So that is what is happening in terms of the solid in particles that they actually do move, but their movement is restricted due to the arrangement of particles restricted because of the spaces available between the particles in metal as compared to the liquid state and the gaseous states which have more availability of free space. So how then are you able to see these spaces? We will look at it later on. Last but not least, that particles are always in constant and random motion, so that it's always moving. It's just the movement. It's not something that is prescribed. In other words, like I do not say that I do a very nice routinely going to places or I tell you where to go. I follow a particular instruction. So that is no longer random. Random means that it's like your own mood. It's based on the mood of the particles. They want to move where also can. Okay, so there is no waypoint or there is no form of direction in which it actually moves. So that's what they meant by random, but it's always moving. Now, in this example, we take a look as to how are we able to see that there is spaces. So number one is we know that we cannot see particles because they're too small. So are we then able to visualize the space? How do we know that spaces do exist? So this experiment helps to show this particular point whereby let's say you take 30 cm cube of alcohol and you add it to 30 cm cube of water. Ideally, you should have 60 cm cube of volume, correct or not? But when you add it all together, you only got maybe 59 cm cube. So what happened to that 1 cm cube? You can't just destroy atoms suddenly by mixing it. So what is actually happening is that the smaller particles tend to fit into the spaces that is available from the metal that has larger particle size. So in other words, right, there's two main inference that you can see. Number one, the size of particles in alcohol is different from the particles in water, such that the smaller particle in size will be able to fall in between to the spaces of the larger particles, not within inside the like this big particle, then you see one small particle inside it. This does not happen. They do not combine together in this fashion. Instead, let's say you have a container that has all these big particles. Then you pour small particles inside. So you realize that the smaller particles are able to seep through these empty spaces. Of course, this is not the accurate representation of the particles. This is just to illustrate to you that where the particles can fit into all these small little spaces and yet retain the same volume of the of the solution. Okay, so the total volume will definitely be lesser than that of the expected volume. However, let's think about it. I change the question from volume now to mass. Let's say I say this is maybe 5 grams. Yeah, 30 cm cube, I would say 50 grams. And now water will also have 50 grams. Okay, when I add them up, okay, when I add both of them up, I weigh them. Ideally, they will get 100 grams of mass. Now the question is, do you think there is any change in mass? What happens to the mass? Okay, can pause the video, think about it. Okay, so what happens actually is that the mass will actually be the same. Why? Because mass is actually accounting the amount of matter of the individual particles. So the number of particles in alcohol and in water, they do not change. Because like for example, you put like pebbles, sorry, you put the particles in one box. You just put more things inside. You're actually adding more mass. The mass do not reduce. In other words, right, it's like you eating. As you keep eating more food, do you lose weight? No, you actually gain mass. So same thing in this case, whereby after you combine, the mass would be the same mass of the food you eat with your body mass. So the mass of the alcohol must be the same with the mass of the water, and therefore they have to be the same. Okay, the mass has to be the same because combining it together will not result in any change in mass. Now, evidence for space between particles. If we do another one, okay, you can try at home, whereby you take a small container, a cup maybe, you throw in beans, then you throw in the rice grain. So all these rice grains, right, are able to fit into the spaces between the rice grains and the beans. And through mixing, right, you actually still retain the same height, more or less the same height, or maybe higher a bit, but the volume will be the same. So this would then suggest that the size of the beans and the rice are different. So same thing like the alcohol, the particle size of the alcohol and the water is different, allowing the smaller particles to fit into the spaces of the larger particles, hence having the total volume of the mixture to be less than the expected volume. So other evidence for different spacing of particles between solid, liquid, and gas is by compressing the object. Because when you compress the object, right, you are actually pushing the particles to be closer to one another. So through compression, so when you increase compression, you are increasing you are actually not increasing, sorry, you are reducing the spaces of the particles. And therefore it becomes like in a way smaller. Now, some of you may ask, okay, so I take rock, I try to squeeze, cannot squeeze, it's not actually being compressed. That's because in a solid, the particles are already so packed that there is very minimal or little space available for other particles to move through it. That's why solid cannot be compressed. Liquid is also not able to be compressed, but it can be compressed in a very, very small amount. Like if you use a lot of strength, you can compress liquid. But in actual fact, this small compression is negligible. Negligible means very small. It's like so small that it means nothing. Okay, but gas, however, in gas, you're able to compress it so much. So this means that in gas, because you can compress a lot, right? What happens is there is actually more spaces in gases. So if I were to draw a diagram, right? So solid, liquid, and gas. In terms of compression, so more compressed to no compression. Okay, so this compression increases from solid to liquid to gas. Okay, then what does this mean? This means that it has more spaces between particles. While over here there is no spaces. So this is one example that you can do. Next, for evidence of for evidence for different spacing of particles in solid, liquid, and gas, the particles in a gas are very far apart. So when we squeeze the balloon, we are actually pushing the particles closer together. And these spaces between the particles are just too small. So we cannot push particles closer to one another when we in, let's say, solids. So basically, how much we can compress really depends on the spaces. So spaces affects compressibility of your matter. Okay. What about movement? So just now we talked about diffusion, right? So diffusion is the process or the evidence to show that particles are able to move. Okay, so there are many ways in which we can actually demonstrate whether particles are always moving. So in this case, we actually use perfume lah. Okay, in which perfume is more or less in a gas. So what happens in a gas, right? In a gas, yeah, in a room where you spray the perfume, maybe at a particular area, it's very strong. So your hand will contain a lot of perfume, concentration of perfume particles. However, after some time, you realize this perfume diffuse across the whole room so that it will actually be at one part of the room that allows, which has initially very low concentration of the perfume particle. So these perfume particles are spreading. And you also realize you cannot control the movement of such perfume particles. They're always in very random motion. Okay, another one that you may want to consider that shows this in a liquid state, so diffusion in liquid state, you can go to YouTube and find maybe the diffusion of copper to sulfate crystals in water. Okay. So what you will see is that initially you have this beaker. So first you have this beaker of water, and in between and inside it you put maybe a solid of copper 2 sulfate, which is water. They have a copper 2 sulfate crystal. So what happened in the copper 2 sulfate crystal is that the most of the particles are mainly, okay, situated at the bottom. But after some time, you realize that the particles will slowly be diffused throughout the whole solution. Okay, where the highlighted blue color shows how the copper 2 sulfate crystals actually spread across or diffuse across the whole spread. So this shows that copper 2 sulfate crystals consist of very tiny discrete particles that have constant and random motion in water. Okay, so this is because after a period of time, these copper-2 sulfate crystals will start to diffuse, which can be observed by the spreading of the blue color in water. Another experiment to show that diffusion of gas actually happens is the use of bromine water. So let me see if I can just add one more page here to illustrate this. Yeah. Okay. So what happened is, imagine you have this particular gas jar, and in between this gas jar you have a paper, a lid actually. So let's say this is a lid, and this whole thing is a gas jar. Okay, where at the bottom, so this is just air, and this is bromine gas. So what happened is, for bromine gas, it is maybe reddish brown in color. So this whole cylinder is filled with the gas, and the air, of course, it's clear. It's more or less transparent. So this is what happened. So what you do is you remove the lid. You remove the lid. What you will realize is the bromine gas will start to travel upwards a bit, okay, towards the area where there is, okay, diffuse upwards to the area where there is a low concentration. So over here you have high concentration of bromine gas, and over here you have low concentration of bromine gas, okay? And this is still air. But then you ask, oh, where does the air move? It actually moves downwards. So while the bromine gas moves upwards, the air actually gets, which are smaller, they tend to move downwards, the particles. Okay, so after a few hours, you will realize that the bromine gas would actually fill throughout the whole gas jar. Okay, this is when the bromine mixes completely in the gas jar, or in both gas jar. Okay, so this is how the whole action of diffusion occurs, where after a period of time you actually remove it. Okay, yeah. So this is for diffusion in gas. And just now we talked about diffusion in liquid using the copper-2 sulfate crystals as an example. Then, okay, so what we have learned is that we have seen how the particulate nature of matter actually helps to move around, in which we use models to understand things that we cannot observe directly. One way, if it's too small, we do the experiment to find out if there is space. So in the alcohol and water experiment, we are able to show that there are actually some spaces between particles. Okay. Secondly, we also want to see the movement of particles, and that's through the experiment of diffusion, where we can see that the particles actually are able to move. Because first question we ask, is there space? And we have verified that there is space through the alcohol and water experiment. Second, we ask, oh, so if I got space now, what can I do with it? What will the particles do with it? Then we'll try to understand how particles move. So that's where the experiment of diffusion occurs. So now that we have already understand how particles move, we also have understand that there are spaces in between. We try to use the particulate model of matter to try to visualize the arrangement as well as the motion of the particles in a solid state, liquid state, and in a gas state. And slowly we will be able to better understand the particulate nature of matter. So this is the segment for now. Slowly pause the video, do a bit of digestion, understanding, recapping of your concepts, and then do remember to subscribe to my channel, like my video, and click the notification button for future video contents. And I'll see you in the next segment where we will be actually discussing on how to use the particulate model of matter to explain the physical properties of matter and its arrangement. Thank you and have a nice day.